Hey everyone, let's check out this very nice example together. Actually, this is a good example because it combines a lot of concepts in physics in one just simple example. So in this example, we have an object that is a charged object with a charge Q, and this Q is equal to 20 nanocoulomb, which is 20 times 10 to minus 9 coulomb, and its mass is actually 1/1,000,000th of a kilogram, so 1/1,000,000 of a kilogram. So it's a very small object, it's a very light object, and it's hung by a very light kind of like string, so its mass is even smaller, so it doesn't matter too much. But because it has a positive charge, this object has a positive charge, and it is within the vicinity of an electric field like this one. This electric field is going from the positive to the negative as indicated. Because of that, it pushes this light object just away enough, and it makes an angle 30 degrees with the parallel plate side. Okay, so now in this example we will need to find the surface charge density on the parallel plate capacitor, and we mean by that by one parallel plate capacitor. Okay, so we found out using Gauss's law in the past that E, the electric field, is equal to the surface charge density divided by epsilon 0. Now the nice thing about this equation is like it's simple. It gives us the relationship between the electric field, the surface charge density. Okay, epsilon 0 is something that should be given to you all the time. So epsilon 0 is equal to 8.85 times 10 to minus 12 coulomb square per Newton meter square. Okay, so this is always given. All right. However, we need to find the surface charge density, and this is surface charge density is unknown. We can't find it. And to find it, we need to know the electric field. Is the electric field given in this problem? No. So we need to find the value of the electric field. Then we plug it back here to find the surface charge density. Okay, well, how do we do that? Well, let's remember this is an object that has a mass, and we are given some like information about it, Q and M. So maybe there's a hint there. Okay, let's draw a free body diagram. It seems that this system is in equilibrium. There's a lot of forces around, so probably it's a good idea to use Newton's law to find the value of the electric field. Okay, let's do that. So to do that, we need to draw a free body diagram for this object. So this object is under the influence of gravity, and the nice thing about gravity is it is always down. Another force that you can see is the tension. The tension is pushing up or pulling up on the object, and it is directed this way, and we need to find maybe this angle or this angle, doesn't matter. Well, how do we do that? If this angle is 30 degrees, this is parallel line to this parallel line, so this angle should be also 30 degrees. So this angle is 30 degrees, which means that I'm going to just take this angle, which is 60 degrees. I like to take angles always with the x-axis, whether it's positive x-axis or negative x-axis. It doesn't matter. And I'm going to call this force tension. Is there another force? Yes, you bet. And the force of electric field coming from the parallel plate capacitor acting on a charged object, and this force, I'm going to just put it like this. This is called F sub electric field. Okay, and the force of the electric field in terms of the Q, the charge, and the electric field is equal to Q times E. And we you can find this when you define this equation when you define the electric field in terms of the force, because here the electric field is equal to the force acting on a point charge, and the same here. Okay, so anyway, so now let's analyze these forces to find the electric field. So I'm going to make a table, and this table here, I'm going to say summation over all the forces acting on the object in the x direction is equal to mass times the acceleration in the x direction. And this is Newton's second law. Summation over all the forces in the y direction is equal to the mass times the acceleration in the y direction. Remember, this object is in equilibrium. Equilibrium means that it's not moving, or it's moving at a constant velocity. In both cases, the acceleration is 0. So this is 0 and this is 0. Okay? So basically, we ended up with summation over all the forces in the x direction is equal to 0, and summation over all the forces in the y direction is equal to 0. Okay, according to this free body diagram, let's see what forces are acting on the object in the x direction. But before that, we need to analyze this little force here, because part of it is in the x-axis and part of it is in the y-axis. All right, let's drop or resolve this force in x direction. If we do that, this force will be equal to t cosine theta, and theta is 60 degrees, okay? And if we drop it here on the y direction, it will be t sine theta, okay? And now we don't need actually this. We don't need this whole thing because we already compensated for it. Okay, let's see what force is acting on the object in the x direction. And for that, let's do this. So this seems to be Fe is positive. So I'm going to say that's the first force in the x direction, and it's positive, going to the positive direction. This is the negative direction. Minus Te cosine theta, and these are all the forces in the x direction. We don't have any else, and that should be equal to 0, which means that the force in the electric field is equal to T cosine theta. Now the force of the electric field, we found it to be equals to Q times E. So Q times E is equal to T cosine theta. I don't think we can dismantle this equation anymore, but the advantage here, the good thing, the good news is that E appeared, and we are looking in this whole thing to find E. So once we find E, we can plug it here and we can find then the unknown charge density, surface charge density. Okay, now let's work on the y direction here. So here we have T, the positive side, and this is the negative side. T sine theta is equal to or minus mg is equal to 0, or is equal to mg. I just consumed one of the steps here, and maybe I should plug in some numbers. I'm going to say here T sine 60 is equal to mg. So here Q E is equal to T cosine 60. Now I'm gonna rearrange this equation. I'm gonna rearrange it so that this right hand side is the left hand side. So I'm gonna say T cosine, you will see that y, T cosine 60 is equal to Q E. After rearranging this equation to look like that, it looks like similar to this equation, as you can see. So just divide the two together. So take this one here. I'm going to write this one here. T sine 60 is equal to mg, and divide it by this whole equation. D cosine T cosine 60 is equal to QE. You can do this in math, okay? So T with T cancels. Sine over cosine is tan. So tan 60 is equal to mg divided by QE. Now, do you know m? Yes, there is m. So m is known. G is 9.8 meters per second squared. Q, the charge, is also known, 20 nanocoulomb. Plug all the numbers in, and you can find the unknown, which is E, because tan 60 you can calculate it in the calculator. So this gives us E. We can find the electric field to be equal to 283 Newton per coulomb. Newton per coulomb. Now take this E and plug it into this equation that we started with. E is equal sigma over epsilon 0. So let's take this here because we have more space here. E, which is 283 Newton per Coulomb, is equal to sigma, what we're looking for, divided by epsilon 0. We know what epsilon 0 is. It is 8.85 times 10 to minus 12 Coulomb square per Newton meter square. And if you do this calculation, cross multiplication and divide, you can get sigma is equal to 2.9 times 10 to minus 9. This is a surface charge density. Surface charge density, surface, so it should be Coulomb per meter square. Oof. And that's it for this problem. Thank you very much.